Welcome back, students, to Unit 2 of Chemistry, the Atomic Model of Matter. Today we'll be talking about the periodic table, and we'll start with a little bit of a history lesson about the atomic model. So we've known about atoms from ancient Rome ago. In ancient Rome, there was a philosopher by the name of Democritus who looked upon the Colosseum and he said, Colosseums are built of bricks, and bricks are made up of mud and straw, and mud is made up of water and dirt, and all things are made up of smaller parts. So Democritus rationalized that all things have to be made up of small, invisible particles, the air of the gods. So he called these atomos, which we have translated over time into atoms. So Democritus coins the term atoms. From ancient Rome up into the modern Renaissance, we enter the age of alchemy. And in alchemy, which was a blend between religion and science, some good science actually happened. For example, our peer review system, where I perform an experiment and you perform an experiment, and if we get the same results, that validates those results. That system came about from alchemy. We also discovered some of the more common elements on the planet: oxygen and hydrogen and phosphorus. And if you were in class, I told you the story about the German alchemist who discovered phosphorus by distilling urine. But it's not until the late 18th century that we get our first chemist, or the first chemistry you need to know for this course. John Dalton was a chemist, a physicist, a meteorologist. He was into all sorts of sciences. For example, he rationalized and documented that color blindness follows maternal lines, and therefore realized that it is your mother who ends up giving you color blindness. And if you have color blindness, the medical term for color blindness is named Daltonism after him. Dalton, after looking over many of the alchemic papers throughout the ages, noticed that atoms followed a set pattern, and Dalton rationalized this pattern by burning things in containers. When he burned things in containers, he found that the mass of the container before and after was the same. So he rationalized that chemical reactions are just rearrangement of atoms, and from that came up with a theory of how atoms work. He said all atoms that behave the same are the same. So for example, the hydrogen in you, the hydrogen in the air, or the hydrogen in plants, or the hydrogen in the sun is all the same type of atom. It all behaves the same way. If you were to turn it into a gas and ignite it, it would make a barking sound. If you could hear the sun, it would be making a constant barking sound, which it's been making for trillions of years. You just can't hear it. All atoms of the same element are identical. They all do the same thing. They all are the same. Atoms can't be created or destroyed. They always combine in whole number ratios. There's always one oxygen to two hydrogens. It's never half an oxygen to one hydrogen, because that doesn't exist. And when we see a chemical reaction, all we're doing is recombining those elements. Now, Dalton's theory holds true for the most part. However, there are some things that have changed. We now know that atoms of the same element are not exactly the same. So for example, hydrogen comes in a couple different flavors. Most hydrogen, about 99% of all the hydrogen you'll ever come in contact with, is hydrogen with one proton with a mass of 1, called protium. However, some hydrogen can get a little heavier. Some hydrogen is known as deuterium. It's a proton with a neutron. Deuterium and protium both exhibit the same chemical properties. The only difference is one has a slightly larger mass than the other. Dalton's theory has another hole in it that we'd figured out in World War II, that atoms can be destroyed. The next big scientist to know for this course is Joseph James Thomson, or J.J. Thomson for short, who is a physicist who led many others to make groundbreaking discoveries in science. He won the Nobel Prize, so did 7 of his students and his son. Thomson was interested in the newest invention of the age, the vacuum. Not the one you clean with, but the one where it's an absence of stuff. Since it was the early 19th century, a true vacuum did not exist, but they were able to reduce the amount of gas in a set container. So he would take these glass tubes and he wanted to see how electricity behaved in a vacuum, quote unquote vacuum. So while it wasn't a true vacuum, it was a partial vacuum, he put an electrical current through it by attaching an anode to one side a negative side, the anode, and a cathode to the other. You can remember that cathodes are positive because cats have paws. Haha, dad jokes. Now, what he found was when he passed an electric current through this partial vacuum, the cathode always released a beam of energy that was repelled by a negative magnet and attracted to the positive end of a magnet, meaning that that beam of energy was negative in some way. Thomson changed out the metals in his anodes and cathodes, changed it for zinc, silver, gold. No matter what metal he placed in his cathode, it always produced the same ray, so this became known as a cathode ray. Cathode rays went on to develop into your modern televisions. Those televisions that you see at like thrift stores where they have that huge back to them, that huge back is full of cathode rays because as this energy comes out, when it strikes a detection plate, it produces different wavelengths of energy, different colors. And so your modern television screen was really a collection of a bunch of cathode rays. From his experiment where all of those metals produced a negative beam of energy, Thomson realized that atoms can't just be spheres of stuff. Those spheres of stuff have to have a negative component to them, which you now know as electrons. He called them corpusculars. But electrons exist in all matter. Now, Thomson knew that you could touch metals and not be electrocuted, so he rationalized that while electrons are negative and float around in the atom, they must be in a sphere of positive energy to cancel out that negative, kind of looking like a chocolate chip cookie. Now, J.J. Thomson was British, and at the time, any dessert in England was called a pudding. Like bread pudding is really just sweet bread. So while we might think of this as a chocolate chip cookie, Thomson called it a pudding, and chocolate was extremely expensive and extremely difficult to get a hold of in the early 18th century, so he wouldn't have put chocolate chips into his cookies. He would have put fruit at the time, so plums. So the plum pudding model, or the chocolate chip cookie model of the atom, was J.J. Thomson's contribution to our atomic model. In my tenure of teaching chemistry, J.J. Thomson appears on every other year's SOL. So there is a high probability that you will see a question about J.J. Thomson on your standardized test, and for that reason, he will be on my test. If I were you, I would know J.J. Thomson discovers the electron and develops the plum pudding model. It also would not hurt to know that he developed the cathode ray, as it has shown up that this exact picture is shown and says, what discovery did this device lend itself to? Discovery of electrons. So I would know J.J. Thomson, electrons, cathode ray, and plum pudding. One of Thomson's students was Ernest Rutherford. Ernest Rutherford is the other big name to know in this course because Rutherford worked with Madame Curie on radiation. Madame Curie was a French scientist who noticed that certain rocks produced a large amount of energy. You could put some rocks next to water and the water would boil. She actually figured out that that rock was emitting the energy, but Rutherford got a lot of recognition for it for figuring out what those rocks were putting out. They were putting out little bullets of atoms. These little bullets of atoms gave Rutherford an idea. If atoms are made up of cookies, what would happen if you broke the cookie apart? So Rutherford set out to shoot these little atom bullets at the cookie, hoping to break the cookie into 1,000 little pieces and get what was inside the cookie. So he hired some grad students to roll out thin foil of gold. Gold is very, very malleable, so you're able to roll it into very, very thin sheets. So he made sheets of gold, and he shot these sheets of gold with these little atom bullets. They set up a detection grid around the sheet that would light up anytime a bullet or some part of the atom would hit it, and this way they'd see what was coming out. However, when Rutherford did this, Most of the atom bullets went straight through the gold without hitting anything. And Rutherford said that was really weird, but the weirdest part was that some of the bullets bounced back. He equated it to be like shooting a cannon at tissue paper and getting shot in the leg. It didn't make any sense to him. So he rationalized that the cookie model, the plum pudding model of the atom, cannot be true because his bullets were passing straight through it without causing anything to come out. So Rutherford rationalized the atom had to be mostly empty space. However, those bullets being deflected back had to be hitting something so incredibly dense that they were bouncing off of it. So Rutherford rationalized there had to be a nucleus to the atom, an incredibly dense core. So Rutherford develops a planetary model of the atom, where electrons orbit the nucleus like a planet. However, Rutherford's planetary model only lasted in the scientific community for 6 days before physicists got a hold of it and said, that cannot be true. All orbits are missing. Well, the International Space Station is constantly falling to Earth. It just misses the Earth every time and then falls again and misses. However, if you keep missing, at some point you will not miss. All orbits decay naturally over time, so every couple of days the International Space Station needs to put a little puff of air out of one side to push it a little further to make sure it misses a little bit more. If electrons orbit the nucleus like a planet, that orbit would eventually decay and it would eventually strike the nucleus and all matter would end. So Rutherford's planetary model doesn't hold up. And it was one of his students, Niels Bohr, that made the connection why the planetary model doesn't work. Bohr was in communication with Einstein and Planck and knew that electrons were both a particle and a wave function. And wave functions cannot fit around a nucleus unless they are a certain distance from it. So you have to have a peak and a trough to make a wave. A peak and a trough could fit a certain distance from the nucleus, but if you had a wave with more energy, you would need that wave function to be further out. So these waves of electrons exist in different energy levels around the nucleus. This was Bohr's contribution, and we have always taught Bohr models in chemistry where you show the nucleus of the atom and then concentric circles that correspond to these energy levels, because drawing these roving wave functions is a little complicated. It's just easier to say. Here, we'll just draw concentric circles to symbolize the different energy levels electrons are found in. Another scientist to know is Robert Millikan, an American scientist who wanted to know the mass and charge of an electron. So he took oil droplets and ionized them. He gave them a charge and suspended them between two magnetic plates. He used a special microscope and a bunch of math to calculate that the mass of an electron is practically nothing, and the charge of an electron is actually substantial comparative to its mass. So electrons have mass, it's just we normally say the mass of an electron is practically zero. But they do have a small amount of mass, and they have a charge that is negative, but if we measured it in volts, it would be itty bitty, so we just say it's a -1. Our current model of the atom is based off the fact that electrons are both a wave and a particle. They exhibit a duality of nature, and if you were in class, you watched the Minute Physics video on the duality of matter. If you were not, please pause the video, go watch that video at this time so that you can understand the wave-particle duality of matter. That wave-particle duality mentioned in the video causes us to have some interesting interactions when we talk about electrons. While two electrons can't occupy the same space at the same time, they can share a wave function. If one is traveling in one direction, another electron can travel in the opposite. So electrons can occupy the same wave function provided they move in different directions, which we'll call spin. One electron could spin up, another electron could spin down. This was done by the work of Wolfgang Pauli and led to Pauli's exclusion principle. We'll talk about Pauli's exclusion principle in Unit 3, but for right now, famous scientists to know, Wolfgang Pauli. The periodic table has its own history. For ages, people kept books, literal textbooks of information about elements, and made quick reference tables or lists where they had lists of the elements. But these lists were never uniform. No one used the same list, and they varied. Some people made lists based on how elements reacted to one another. Some people made lists on what elements reacted with which. Some people made lists based off of mass. And one of the most famous people to do so was Mendeleev. Mendeleev built his periodic table based off of mass. However, Mendeleev started to notice there was a repeating pattern to the periodic table when you list them by mass. And so when he came across a space where the masses didn't line up, where it didn't go 1, 2, 3, the relative masses didn't line up, he left spaces in his periodic table for elements to be discovered in the future. The TED Ed video linked on the PowerPoint is a great history lesson in Mendeleev. It is important for you to know that Mendeleev made his periodic table based off of mass. I remember Mendeleev has 2 E's and mass has 2 S's, and that's how I keep them straight. Our current model of the periodic table is built off of nuclear charge. The charge in the nucleus is done by the work of Robert Moseley. And that will be the end of our little history lesson. Our current model of the atom, the quantum model, has electrons in different energy levels or wave functions around the nucleus, and those wave functions have different shapes. In Unit 3, we'll talk about what each of these shapes mean and what the wave functions are. For right now, I'm just happy that you know some history. You're now able to answer the first 4 note quiz questions for Unit 2.2. Pause the video and complete questions 1 through 4. So based off the work of all the scientists we have seen, we now know that protons are found in the nucleus. The nucleus has a positive charge, and electrons are found around it. And between the two, there is a vast amount of empty space. If, for example, the sun was the nucleus of an atom, the nearest electron would be Pluto, would be the nearest possible electron. So electrons and protons are separated by an incredible amount of space. The nucleus is not just protons. Since protons are positive, 2 protons next to one another would repel one another. They would not get along very well. So, to ease their burdens, between protons you tend to find neutrons. Neutrons are very similar to protons, except for they have no charge, so they separate them. Protons and neutrons are found in the nucleus, and together they make up almost all of the mass of the atom. Protons and neutrons are the only things that we will consider the mass of the atom. Electrons have no mass, but they take up the most space. The volume of atoms is held pretty exclusively by the electron cloud. This is why the nucleus of an atom is so dense. If you were to remove the electrons from all the atoms in humanity, all humanity would fit in about a teaspoon, because the protons and neutrons take up so little space. So remember, when we talk about the periodic table, the rows are known as periods, the columns are known as families, and we arrange them in increasing nuclear charge. The whole number in each one of these tiles is the charge within the nucleus. So let's get comfortable with looking at periodic tiles. So the name of elements is in English are fairly straightforward. Some do come from antiquity, which is why some of the symbols don't match up. Some of them make sense. Calcium is Ca, and oxygen is O, and hydrogen is H, but then you have some that have their names based off of Latin. For example, tungsten is W for its Latin name Wolfram, or lead elemental symbol is Pb for Plublum, or copper is Cu for its Latin name cupric. Elemental symbols and names don't always match up. As we move through the year, you will You will get more comfortable with the symbols that don't perfectly match the names, but if you ever have a question, feel free to come up and ask me, Professor, what is element W? And I'll be like, oh, that's tungsten. Its Latin name was wolfram, because I'm nerdy and I know those things. As we said, the whole number on each tile is the atomic number, or the nuclear charge. Nuclear charge is given the variable z, so sometimes you'll just see me write z equals for what the nuclear charge is. The charge in the nucleus is exclusively the number of protons. Each proton is a +1, so calcium with a nuclear charge of 20 really means that calcium has 20 protons, and it's ultimately the charge in the nucleus that determines what the element is. Any atom with 20 protons automatically is calcium. Any atom that has 21 protons would no longer be calcium, that would be scandium. Or if you have an atom that has 19 protons, you now have potassium. The number of protons is ultimately what determines what the element is. As long as an atom is neutral, if you see a symbol and there's no number in the upper right hand corner, that means that the atom is neutral. If you see a number, it means that it is an ion, it has a charge. But if no number is present, that means that the atom is neutral. In order to be neutral, for every positive, you would have to have a negative. So as long as an atom is neutral, the number of protons equals the number of electrons. But that's only if it is neutral. If you develop a charge, they are no longer the same. They would change the number of electrons. But that's a story for a different day. The decimal point number on the periodic tables are the average atomic masses. They're a weighted average of all the known isotopes of that element. For today's lesson, let's round these to the nearest whole number. So for calcium, 40.078, let's just call that 40. The average atomic mass, the mass of an isotope, would be the number of protons plus the number of neutrons. If you see an element whose mass is in parentheses, that means there are no stable nuclei of that element. There are so few atoms of it that we have yet to quantify what its mass is on average. With that being said, you're able to answer the next 3 note quiz questions. In your packet, pause the video and answer 5, 6, and 7. As we talked about in the history, isotopes are the same element, just different masses. The number of neutrons changes. We often write isotopes with their mass number after the element name. So for example, protium is actually hydrogen 1 and deuterium would be hydrogen 2. The mass number changes because each one just changes the number of neutrons. An isotope is the same element but with different number of neutrons. You will be surprised the number of SOLs, the number of test questions I have seen that ask a very simple question: how are isotopes different from one another? They change the number of neutrons. Please, please, please remember this. We can denote isotopes of different elements by writing an isotope notation, where we write the elemental symbol with a sort of fraction in front. It is not a fraction, it is actually a superscript and a subscript. The superscript is the mass number and the subscript is the nuclear charge. So turn in your packet to exercise 1. You'll notice something's missing from these isotope notations. The nuclear charge I did not give for each of them. That's because it's usually understood. Anything that is a carbon automatically has a nuclear charge of 6. So it's kind of redundant to put it. Isotope notation does not necessarily require nuclear charge. However, it is good form and good practice to include it. So for carbon, let's complete this and say carbon 14, its nuclear charge is 6. So speaking of that nuclear charge being 6, any atom that is carbon has to have 6 protons. Its nuclear charge is 6. And provided that this element is neutral, I don't see any charge present. There's nothing in the upper right-hand corner. That means that it is neutral. If I have 6 protons, I have to have 6 electrons to cancel it out. To determine the number of neutrons, I simply subtract the number of protons from the mass, because the mass of any element is simply the number of protons plus the number of neutrons. So carbon 14, if I subtract 6 from 14, I get 8. Carbon 14 has 8 neutrons. Carbon 14 is an isotope of carbon. Another isotope of carbon would be carbon 12. It is still carbon, so its nuclear charge is still 6. And as long as it's neutral, it still has 6 electrons. But what changes is the number of neutrons. If I subtract 6 from 12, I get that the number of neutrons here in carbon 12 is 6. Chlorine 36. Chlorine is element number 17 on the periodic table. So in being element 17, its nuclear charge has to be 17. And since this atom is neutral, there is no charge in the upper right-hand corner. This has 17 electrons. To determine the number of neutrons, it's simple subtraction. 36 minus 17 is 19 neutrons. You'll notice that zinc 68 is different than all the other examples we've done so far. By being zinc with an atomic number of 60, we do know that zinc 68 has 30 protons. However, notice that zinc 68 is an ion. We have a charge here. The charge of an atom is the difference between the protons and electrons. By having a +2 charge here, we now know that there are less electrons present, 2 less to be precise. So the number of electrons for zinc 68 would be 28. The number of neutrons for zinc 68 is still found the same way. 68 minus 30 is 38. Zinc 68 would have 38 neutrons. With that being said, you are able to finish your Unit 2.2 note quiz questions. I would also like you to do page 15 in your packet. If you are present in class, I would have given you practice 3.1. If you are not, you can practice on page 15. On page 15, there are no ions, meaning all of them are going to be neutral. So your nuclear charge, the atomic number, and number of protons will always be the same. And for this worksheet alone, the number of electrons will always be the same. These 3 columns should always be the same on page 15. In class, that won't be true for practice 3.1. It's a little more complicated. If you would like to get the practice for 3.1 and we're not in class, you may email me or see me during your lunch or after school. With that being said, finish your note quiz questions, do page 15 in your packet, and next time we will look at the average atomic mass in much greater detail.